Welcome to the lesson on image segmentation with Matlab. In this lesson, we will learn how Matlab can be used for image segmentation tasks. What is image segmentation? Segmentation is the process of locating items or regions of interest in an image. For example, image analysis algorithms for self-driving cars would benefit from locating pedestrians, vehicles, or other potential obstacles in images acquired from the onboard camera systems. Image segmentation algorithms could be used to locate pedestrian and vehicle traffic in such images. Then the location of the objects of interest can be used to plan the next set of instructions for the self-driving car. For example, to apply the brakes and stop to avoid a collision. In the field of medical image analysis, segmentation is critical in many applications, such as detecting abnormalities or lesions in magnetic resonance imaging. An example MRI scan is available in Matlab in the MRI.TIFF built-in image. Detecting such lesions is critical to help physicians diagnose and plan treatments. Segmentation is highly related to classification, such as the data classification methods we learned about in Lesson 2. Recall from that lesson we considered our data samples as features of some process, and our goal was to partition our feature space to determine a classification for each data point based on what partition of the feature space in which it falls. Segmentation can also be formulated as a pixel classification task. Consider Matlab's cameraman.tiff. If we think of each pixel in this 256 by 256 pixel image as a data sample, and our image array simply as a large vector of intensities containing over 65,000 independent samples of our intensity feature, we can imagine designing a data classifier that partitions the intensity data space to classify each intensity sample, which happens to correspond to each individual pixel. Most often this is a two-class classification problem. We wish to classify each pixel as belonging to the foreground class or the background class. For example, if our goal is to segment the cameraman from the rest of the image, pixels in this region indicated in red correspond to foreground because they are part of the cameraman region, whereas pixels in the region indicated in green are part of the background class because they are not part of the cameraman region. The simplest pixel classification method is called thresholding. With thresholding, we consider the intensity assigned to each pixel as a one-dimensional dataset. Thus, the values for our pixel intensity feature set range along a one-dimensional axis as shown here. With thresholding, we partition the one-dimensional data space of pixel intensities into two classes. One class is defined where image pixels have an intensity greater than the threshold value, and another class is defined where image pixels have an intensity less than the threshold value. Thus, again, relating this back to the data classification techniques we learned in Lesson 2, thresholding an image is akin to treating each pixel as an independent intensity sample and classifying each sample using a partitioning of the intensity feature space defined by a chosen intensity threshold value. The foreground class can either be class 2 if the foreground corresponds to brighter intensities, or class 1 if it corresponds to darker intensities, and vice versa for the background class. Thresholding makes sense when the foreground regions of interest are consistently higher or lower in intensity than the background. For example, consider our cameraman image. We want to segment the cameraman and camera from the rest of the image background. A simple thing we can try first is thresholding. We note that the cameraman and camera are relatively dark in intensity compared to the rest of the background regions of the image. So, we can try to find an intensity threshold value such that all pixels with intensity less than the threshold are classified as foreground, and all pixels with an intensity greater than or equal to the threshold value are classified as background. A common way to choose the threshold is using the image histogram. Recall the histogram counts the number of pixels with different intensities and shows which intensities on the x-axis, for which there are lots of pixels taking that intensity, as high counts shown on the y-axis. From this histogram, we can see that there is a large contingent of pixels with a very low intensity close to 0, and another large contingent with intensity from around 100 to 200. Comparing to our image, we see the high intensity portion must be mostly our background class, and the low intensity portion must be mostly our cameraman foreground class. So looking at the histogram, perhaps we find the low point between the two distributions, which is an intensity around 75, and call this our threshold between our fore and background classes. Oftentimes, the fore and background are relatively homogeneous, and thus a good threshold can be chosen by finding the low point between the two distributions in the histogram. Once a threshold is selected, a classification can be performed, and the result can be stored in a new binary image representing the segmentation. We typically display the foreground class as white pixels and the background class as black pixels. This segmentation image is sometimes referred to as a segmentation mask, or sometimes a binary image generally is referred to just as a mask. If we choose a threshold value of 75, shown here is the resulting segmentation mask we produce when thresholding the image. As we can see, in this example, thresholding is able to produce a segmentation mask that to a large degree corresponds to the cameraman, camera, and tripod. It is by no means perfect, but depending on how good our accuracy needs to be for our application, it may be good enough. If it's not good enough, we will see that thresholding can be one step of a sequence of processes to produce a more accurate segmentation. Quantifying accuracy of segmentation algorithms is beyond the scope of this course, but we can appreciate a basic understanding of how accuracy can be quantified for pixel classification. Similarly to data classification accuracy, we can compute the classification accuracy rate of our estimated classification against a ground truth segmentation if one is available. We don't have a ground truth here to quantify accuracy, but we can use this example to discuss pixel classification error types. Pixels that are cameraman and classified as foreground are called true positives. They are positives because the algorithm identifies these pixels as foreground, and they are true positives because the algorithm is correct. False positives are seen in the buildings on the horizon and in some scattered pixels in the grassy areas. The algorithm falsely identifies these as foreground. True negatives, the algorithm correctly identifies as background, such as large regions of the sky or grass. Finally, false negatives are pixels the algorithm incorrectly identifies as background, such as the cameraman's face and neck. Segmentation accuracy is maximized when we have a high rate of true positives and negatives and a low rate of false positives and negatives. Sometimes minimizing the false negative rate is more important than the false positive rate. For example, we really don't want to miss malignant tumor tissue when localizing tumors in medical images, because it would be bad if both the algorithm and the physician don't recognize a tumor. Whereas false positive errors will be easier for the physician to catch and disregard. Or in the self-driving car, since safety is paramount, we would rather the self-driving car incorrectly think there are more obstacles than there really are due to false positives, than no obstacles at all due to false negatives when planning the car's next actions. So accuracy requirements for segmentation are highly application specific. In the remainder of this lesson, we will explore thresholding and edge detection for region and boundary segmentation as our basic set of tools for image segmentation. We will see multiple common ways to visualize segmentations and to remove noise in segmentations. Finally, we will also explore some of the built-in apps in Matlab for segmentation tasks. Thresholding is the most basic segmentation method, and that is where we will start. Let's go to Matlab and see how this works. First, let's read in our cameraman.tiff image using imread. We can display it in a subplot out of a 2x3 grid of subplots using the image function and set our color map to gray. Next, let's compute our image histogram to assist with determining a threshold. Can display the histogram in a second subplot. Just as we saw before in the slides, the histogram shows two distinct distributions of intensities, with many bright pixels and a large contingent of dark pixels, with this region of intensities from around 25 to 100 with very few pixels. So we can look at the histogram and visually determine a threshold, or we could do it automatically. Matlab has built-in functions to automatically determine a threshold. A classic histogram-based method is called the OTSU method. This method aims to find the threshold that separates the histogram into two distributions that have minimum intra-distribution variance. To try it out, we just need the histogram as a vector. Calling the imhist function with no output arguments displays the histogram, but we can call it again with an output to have the function output the histogram as a vector. Then we can find the OTSU threshold by using the OTSU thresh function with the histogram as input. The function assumes that the intensity range represented by the histogram ranges from 0 to 1. And since our image intensities actually range from 0 to 255, we just need to multiply the result by 255 to obtain our OTSU threshold, which we see is 88. We can also display it on our histogram plot. We can use plot to draw a vertical red line at the threshold value. The two ends of our line will have x coordinates at the threshold value. And y coordinates we can range from 0 to some very high number. Some number higher than 1,000, let's say 2,000. And we can plot that in red. Oops, missed a 1. Finally, we can also look at a segmentation mask created using this threshold to visually inspect the results. We define our mask as being all pixels of the image that have intensity less than threshold times 255, and we can display this mask. We see that the OTSU auto threshold method does a quite reasonable job of segmenting the foreground cameraman and camera from the background. It's obviously not perfect, with a number of false positives in the grass and sky and buildings, and also false negatives. But given the simplicity of the method and the fact that it uses no spatial information, treating each pixel entirely independently, it works surprisingly well. So what exactly do I mean when I say it treats the pixels independently? Since with thresholding the pixels are treated independently, this means that the spatial organization is meaningless, which means we could entirely reorder the pixels and the threshold we choose would be unaffected. Let's demonstrate. First, we concatenate our image into a long array. Then we sort the array from the low intensities to the high ones and reshape the resulting vector back into a 256 by 256 matrix to create a new image that we call image reorder. In a new subplot, we display the result. Before discussing it, let's also display next to it the histogram of the new image. We see that the new image has exactly the same histogram as the cameraman image. While the two images look nothing alike, the second image contains exactly the same distribution of intensities as the first, just in an entirely different spatial arrangement. Since the histograms are the same, an auto-thresholding method would arrive at the same solution for both images. Thus, we say such methods are independent of the spatial distribution of pixels. It's not that the spatial information is unimportant, quite the opposite. It is quite useful and typically should not be ignored. However, the advantage of thresholding is its sheer simplicity. Methods that take spatial information into account quickly become very complex. Whereas with thresholding methods, we simply operate on the histogram. One relatively simple thing we can do to incorporate some spatial information into the process is to use low-pass filtering to try to remove some of the small, isolated, noisy pixels in the segmentation. This leverages spatial information because we assume foreground pixels that are all alone are false positives, whereas regions where large numbers of pixels are grouped together, we can safely assume are true positives. These are good assumptions if our foreground class includes larger, more homogeneous objects. In this case, we would not expect foreground pixels to be all alone. We can define a Gaussian filter using the fSpecial function. With a filter width of 30 and a sigma of 5. A rough rule of thumb is to choose sigma such that objects with smaller diameter in the segmentation we would consider to be likely false positives. So here we want our foreground structures to have a diameter of at least around 5 pixels. We convolve our mask with this filter. And we can display the results. We can see in the resulting filtered image that narrower structures have been dimmed by the filtering, but the larger structures are still bright. We need to re-threshold the filtered result. This threshold is again an adjustable number. Let's try 0.5. And we'll put this in the 5th subplot. So we can see this erases many of the smaller objects in the segmentation mask and smooths the edges on the objects that remain. It also has the effect of filling in some of the false negative holes. For example, around the cameraman's neck. Another common spatial information approach is to use what's called connected component analysis. Connected components are the different regions of foreground pixels that are separated by background pixels. For example, here we have a total of 1, 2, 3, 4, 5, 6 connected components. These are these white groups of foreground pixels that are separated by dark background. A common approach is to assume the true positive components should be of a certain size. That is, the number of pixels in each connected component must be larger than a certain amount. Matlab has a built-in connected component function called bwconComp for black and white connected components. We simply give it our current mask as input. The output is a struct that I called comps that contains a subfield numObjects, which tells us how many connected components it found, which is 6. Then there's the pixel IDX list field, which is a 1x6 cell of vectors. One vector for each connected component in the segmentation mask. Each vector contains a list of the indices to the set of pixels that compose that component. So we can determine the number of pixels in each component as the length of its pixel IDX list vector. We can just use a for loop, looping over the number of objects in comps to print to the screen the length of the pixel index list. For the ith component in the cell array. We can see the first component is quite large, being composed of almost 15,000 pixels. The others are composed of a few hundred or fewer pixels. So clearly the first component is our cameraman component, and the rest correspond to the false positive regions that we would like to remove. We can define a new segmentation using just this largest component. We can initialize it as zeros, the size of the mask, and then indexing it at all of the pixels in the pixel ID list for our first component. We can set the value in the segmentation mask at all of these pixels to be equal to 1. These are the pixels for the first connected component, so we are in essence, we are erasing all of the other connected components from the image. Then we can display the result. We can see we have removed all the connected components except the largest one. It's a little difficult to see how it maps back to our original image. Another way we can visualize a segmentation is by visualizing an isocontour separating the foreground and background. This is essentially a way to plot all the little line segments that would be necessary to form a contour separating the white and black parts of the segmentation mask. While it may sound complicated, it's actually very simple to do. We return focus to our subplot for our original image, which is our first subplot, and we call hold on. Then we use the contour function to draw the contour. The first argument is the segmentation mask. Then we specify our desired ISO value. This is the image intensity at which the contour should be drawn within the segmentation mask. To separate the foreground with a value of 1 from the background with a value of 0, we draw a contour at the ISO value of 0.5. We put it twice in a vector like this to do this. You actually can have the contour function draw contours at several ISO values simultaneously, and the vector input permits doing this. You can learn more by typing help contour. Here we just want one contour, so we just simply put in 0.5 twice. Finally, we say what color we want. I'll draw it in red. Thank you, Matlab. That would be the correct spelling for contour. With this visualization method, we overlap the segmentation on the image, making it much easier to see how accurate or inaccurate our segmentation is. This is often a much more useful way to visualize a segmentation than by simply visualizing the binary mask separately. We see overall quite good agreement, but with some obvious false positives and false negatives. Depending on our application, the accuracy of this result may be sufficient. Another approach for attacking segmentation problems is through the use of edge detection methods. Edge detection finds the strong boundaries in the image. Presumably, objects of interest are relatively homogeneous and are separated from the background by strong edges. So, the strategy with edge detection is to delineate objects by their boundaries. The most common edge detection method in Matlab is the so-called canny edge detection method. It's built into Matlab in the edge function. We call edge with image as the first argument, and the second argument is canny, to let the edge function we want to use the canny edge detection method. We'll output the result in image canny. And let's inspect the results in the second subplot, replacing the histogram. Looking at the result, feel free to pause the video to take a few minutes to appreciate the results. We can see the method is quite adept at locating edge information in the image. As such, edge detector results can be useful when trying to resolve the boundaries between different image regions. There are a number of parameters that are optional with the edge function that can change the behavior of the canny edge detector. There are also other edge detection methods built into the edge function. As always, type help edge for more information. Next, let's switch gears and see what we can do with basic segmentation methods for color images. Let's reload our peppers image. Using the imread function and display it. Let's say we want to segment our peppers from the purple background. One feature that should help is the hue feature, as the background is purple, whereas the peppers are all green, yellow, and red in hue. Let's repeat our display of the HSV channels of the image, but rather than repeating all of the code from lesson 4.3, here I've copied the block of code we used in that lesson into a script that I call lesson 4.3 HSV figure. So running the script, we see the HSV channels and their histogram distributions that we generated in lesson 2.3 displayed on our figure. In our hue histogram, we see the magenta class, which should correspond to our background in our image. We also see a lot of red content, which is awkwardly split around the left and right sides of the histogram. Then we see the orange, yellow, and green content here, with a big gap between the green and the magenta. In this situation, the fact that the hue histogram is a circular histogram, where the lowest and highest values both correspond to red, poses a problem for automatic thresholding methods. We will see this if we try to use the Otsu threshold method. We output the histogram from IMHist for the first channel, the hue channel of the HSV image, multiplied by 255 and rounded to the nearest integer. So this converts our HSV hue channel, which are doubles that range from 0 to 1, into integer numbers that range from 1 to 256. And our 256 channel color map tells IMHist what the bins should be. That outputs our histogram in the HST variable. And then we can use the Otsu threshold function to find a threshold for the histogram, which, when multiplied by 255, results in a threshold of 125. This result, a threshold of 125, is perfectly reasonable if this was a non-circular histogram. We have a huge gap between the left and the right parts of the histogram, so a threshold right in the middle would make sense. Except that with a circular histogram, the right side is connected to the left. So having one threshold does not make a whole lot of sense. With a circular histogram, we actually need two thresholds to divide the histogram into two classes. When we have an empty region of our histogram, the best thing to do is to translate our histogram values such that the empty region corresponds to the lowest and highest values. We can shift the histogram and produce H-shift by adding 0.5 to all the hues and computing the modulus of the result with respect to division by 1. So, any numbers higher than 1 that fall in the 1 to 1.5 range after we add 0.5 to our hues are mapped back to the 0 to 0.5 range. This is exactly the same thing as rotating our color wheel by 180 degrees. We can plot our shifted histogram in a new figure. Using IMHist with the rounded histogram that's been shifted, multiplied by 255 plus 1 for the first input. For the color map, we can shift our color map the same way we have shifted our hues. Our color map color wheel can be rotated 180 degrees by putting the entries 128 to end out of the 256 colors in the front, followed by colors 1 to 127. With our shifted histogram, the cyan colors that were in the middle of the histogram before now fall at the first and last entries in the histogram. So now the left and right sides of our histogram both correspond to cyan. and the red colors, which were at the borders of the histogram, now fall in the middle. Now we do not have the issue of a dense portion of the circular histogram being split across the highest and lowest values, and so standard non-circular histogram thresholding algorithms can work. Recomputing the histogram, but this time outputting it to a variable, we can run the Otsu method again. And we find a threshold of 116, which falls around here in the histogram. So we can see we have indeed found a threshold that separates the magenta colors here from the remaining hues in the image. To map this threshold back to the original unshifted hues, we simply divide the threshold we've found, 116, by 255 and add 0.5 to it. Adding 0.5 rotates our color wheel back by 180 degrees. Now we have two thresholds. Thresh 1 is at around 0.5 and threshold 2 is at around 0.95. These two thresholds can be used to bracket the background portion of the hue histogram. And since the hue histogram is circular, defining two hue classes requires two thresholds, since the hue of 1 wraps back around to the hues of 0. So we define our background mask as being equal to 1 for all pixels where the hue channel is greater than or equal to threshold 1, and the hue is less than threshold 2. Our foreground will be the logical inverse of the background. Coming back to figure 1, we can display the result in a second subplot. And we plot our foreground segmentation result. We see that using intensity thresholding techniques on the hue histogram, we obtain a very reasonable approximate segmentation of the foreground and background. For some color images, the hue channel might be the best option for thresholding. For others, the saturation or intensity channels may be the better options. For some, using a combination of the different channels might make more sense. For example, if we wanted to separate the peppers from the garlic bulbs, we can note that the garlic bulbs, here and here, both have very low saturation. And so this small, low saturation component of the histogram likely corresponds to the garlic bulbs. And so the intensity of the saturation feature would be useful for that segmentation task. Finally, some basic segmentation and other image processing tasks can be done not only in code, as we've demonstrated here, but also using some of the built-in apps that are in Matlab. Not all apps are available in Matlab Online, so next we're going to switch to the desktop version to show how these apps work. This is the desktop version of Matlab version R2020A. It should look quite similar to the Matlab Online that you've been using. On the desktop version of Matlab, we have a tab here at the top called Apps, which gives you access to a number of different apps based on the toolboxes that you have installed on your computer. Before we open the app, let's load in our peppers image. And our cameraman image. Okay, so we have our images in our workspace. When we open the app, what we'll see is the app will have access to images that are in the main workspace. So by clicking the arrow on the right, again, we see all of the different apps that come in the toolboxes that we have installed. We're going to look first at the Color Thresholder app under the Image Processing and Computer Vision toolbox. Here, a new window pops up that I can resize to fit on the screen here. Which is our Color Thresholder app. Within the app, the first thing we do is load our image. And we can load it from a file, or we can load it directly from our workspace. Or you can acquire an image from the camera. We're going to load an image from the workspace. This is the Color Thresholder app, and even though we have two images available in our workspace, it's only looking for image matrices that have all three RGB channels. So after we select it, Matlab displays the image, as well as scatter plots of the pixel data in 4 different color spaces. We've played with the RGB color space and the HSV one. I will let those who are interested investigate the 2 other color spaces to learn more about those. The 3D scatter plot shows a point for each pixel with its coordinate position in the 3D RGB system on the left. We have a 3D HSV coordinate system on the right of that, and again, a data point for each pixel is shown. And the 2 other color spaces to the right of that. These 3D plots, similarly to our displays of the RGB and HSV histograms, give a sense for how many separable classes of colors there are in our image. For instance, the magenta component looks to be the one that's the most easily separable from the rest, based off of HSV coordinates in this HSV coordinate system. So let's choose the HSV color space. In this view, we have our 3 histograms. The saturation and value histograms you probably recognize from before. But for hue, Matlab provides a fancier circular histogram, which is much fancier than the one that we implemented in our code. It also permits interactively choosing 2 thresholds necessary to segment the image by hue. So with your mouse, you can grab one and the other threshold, and we can choose to segment the image by thresholding the hues such that we retain all of these hues while removing all of the magenta hues. And we get a very nice segmentation of the image. We can apply simultaneous thresholds to multiple histograms. For example, if we increase the minimum saturation threshold, we can essentially remove the garlic bulbs from the image. We also have tools to create much more complicated thresholds in 3 dimensions. So let me reset the thresholds here. So again, this is a visualization of every pixel in the HSV color space. And what we can do is we can use this polygon tool to draw a contour around a region of the 3D color space. That's going to be a much more complex thresholding approach than could be done by single thresholds on the HSV channels independently. So you close the contour with double click. And what you can see is we've drawn a contour around the magenta pixels in our color space. And so by default, those are the pixels that are retained as foreground. If this is really the background, we can click this button that says Invert Mask. And we can see, again, we get a really nice segmentation of the foreground from the background using this approach. We can also draw a contour in the image space. So using the drawing tool here, you hold down the left mouse click and you can draw multiple contours. When you release that mouse click, it closes the contour. And again, it assumes you're localizing the background. So if we invert our mask, this is the result. When we draw on the image contours like this, what Matlab is doing is it's determining the two hue thresholds in minimum and maximum saturation and value thresholds that correspond to all the pixels that fall within the contours. So it's not nearly as complicated of a thresholding algorithm that is necessary when you draw a polygon in the 3D color space, because it's simply choosing minimum and maximum hues and minimum and maximum saturation and values. At any time, we can also look at a binary representation of our mask. And after you've played with your segmentation for a while and you're happy with it, you also have the option to export. You can export the resulting image, or you can export a function that implements the thresholding algorithm that is being applied to the image. Next, let's look at another app. Now we'll look at the image segmenter app. Again, this pops up with another window that I can resize to fit within the screen here. And again, the first thing we do is to load an image from our workspace. We'll load the cameraman image. We see the image displayed. We see we can threshold the image. So this screen shows a automatically selected global threshold using Otsu's global threshold algorithm, or there are manual thresholding options. The colored image shows the preview foreground, or we can look at the binary mask to see the foreground versus the background using this threshold. And when we're done, we click Create Mask. We can also create another segmentation using more sophisticated algorithms, such as the graph cut method. We won't go into details about how graph cuts work, but how to use them is pretty simple. We ask the user to provide some seed points that define the foreground of our segmentation, as well as the background. So we have these mark foreground, mark background buttons. And we can provide a pretty coarse marking of the foreground and background. And you can see once we have some foreground and background marked, the graph cut method can come up with a segmentation based off of those input seed points. What it's trying to do is it's attempting to find a segmentation that follows the strong edges that separates the user-supplied foreground and background seed points. And also where the foreground and background regions of the segmentation have intensity distributions that match those of the pixels that belong to the marked seed points. So we can see with relatively few button clicks we can actually get a pretty nice segmentation of the cameraman image. And another nice feature of the graph cut is that it's not prone to creating small noise pixels, so you don't see a lot of little false positives and false negatives scattered throughout the mask like we would with thresholding. When we're done, we can create the mask. And there's a number of other tools that you can play with to try to refine the mask. For example, the active contour method. This is an iterative method, so you can choose the number of iterations, and you have some control over the features that it uses. But once you're happy with your parameters, you hit evolve, and it evolves the contour. And we can see we get a different result. And whenever you're done, you can export. So we both can export the resulting image, or we can also generate a function that could be used to create this binary segmentation for this image or any other input image using the same sequence of processes. Matlab has a number of powerful apps like these for not only image analysis but also data and signal analysis tasks. So I encourage you to explore the other apps that are available to you. To summarize, there are many different powerful image segmentation and other image analysis methods built into Matlab. We tried several, including thresholding, linear and nonlinear filtering, and interactive methods using built-in apps. You now have experience with image analysis methods in Matlab. This concludes our lesson on Introduction to Image Analysis with Matlab. For further reading, and for a more in-depth and theoretical presentation of image analysis techniques, I recommend the text shown on this slide. This also concludes our lecture series for this course. The final week of the course is dedicated to completing the course project. If you followed along with the lectures and exercises, congratulations! You now have experience in basic data, signal, and image analysis techniques in Matlab. Note that you can find many more methods built into Matlab than we visited in this course by consulting the Matlab documentation and help pages. Also note that many data, signal, and image analysis methods are not built into Matlab. But the Matlab user community is large, and quite a few methods and functions are coded and posted by community members on the Matlab Central File Exchange. If there is a method you want to try that you don't find built into Matlab, MATLAB Central is a great resource to check to see if anyone else has implemented it and publicly posted the code. I hope you've enjoyed this introduction to data, signal, and image analysis, and that this course serves as a first step towards more in-depth exploration of these exciting topics.